buttons I have to press. Okay, so if this, thank you for intervening, yeah, but next time, do this more quickly, yeah. otherwise we are. Okay, I'm very sorry for this. So it should be started now.
Yes, Professor, it's working now.
Okay, so I'm very, very sorry. So okay, I'll briefly wrap this up. So we have the content equilibrium. So lecture number 2 in Introduction to Lattice-Boltzmann. We have the the content of today is the equilibrium function BGK and moments. And with the equilibrium function, and for this we recall what we had in the first lecture, which was the Isar theorem. Yeah, so Isar was defined like this equation here. Now, see even more technical problems. So this is the definition of the of eta. Then we said that eta is always smaller than always smaller or equal than 0, and for eta, the time derivative of eta is always smaller or equal to 0, and if it is 0, it is at equilibrium. So, and now we derived last time this equation here, for the time derivative, and this time derivative, this here will be 0 if for all velocities, say x1 and x2, we have the following condition. And now let me continue here, where I started to write. Okay, where let me delete this again so that I can start freshly. So, okay, this integral here, you see, this integral up here will be 0, obviously, if this here is 0, right? So this means that F1, no, this is the wrong button again. So F1 after collision times F2 after collision, minus F1 before collision and F2 after collision. If this is 0, then we are in equilibrium, okay? Which you can very, very easily see that this means that F after collision 1 is F after collision 2 equal to F after collision, before collision times F2 before collision. And this, you can easily see, is equivalent to saying that the logarithm of F1 before collision plus the logarithm of F2 before after collision, yeah, is equal to the logarithm of F before collision, F1 before collision, and the logarithm F2 before collision. Yeah. Okay, so this is pretty simple. Yeah, and now we had Boltzmann. Boltzmann proved that this leads to a particular form in equilibrium. In this paper, which was actually, I should give the date. So this was in 1872, and the title of this paper is a little long. So this is the way they wrote papers back then. Weitere Studien über das Wärmegleichgewicht unter Gasmolekülen. And in this paper, Boltzmann proved a conjecture by Maxwell. Conjecture by Maxwell. This is why the equilibrium distribution is actually called the Maxwell distribution and not the Boltzmann distribution. So Maxwell already assumed 20 years or 25 years earlier that the equilibrium had a certain form, but he was not able to prove this, and Boltzmann actually proved this. So Maxwell assumed that this is of the form. So the logarithm of f is equal to some a plus some vector b times the velocity of the particle plus some scalar c times the square of the velocities. Now let's see whether this actually works. Yeah. Take the left-hand side of the equation that we had here. So let's call this guy here. Let's call this guy here equation 2.1. Okay, so take left-hand side 2.1, and this is the logarithm of f1 before collision plus the logarithm of f2 before collision. So there is a constant a, yeah. So this constant a comes twice, plus there's b, okay. So this will be the velocity of the first distribution plus the velocity of the velocity of the second distribution. Second. So, and of course this is scalar plus, now comes the c, the xc1, 1 plus xc2 dot xc2. Okay, so this is what we have for the left-hand side, and suppose we look at the right-hand side of 2.1, then of course we have L, the entire thing after collision, which looks like this. So, okay, the constant was obviously independent. Then we have something like b, and now this goes with the velocities after the collision. Here's some c, so 1 after collision, c1 after collision plus c2 after collision times, so the dot missing, c2 after collision. Okay, so this is what we have. And now, do you, okay, yeah, you're right. So you wrote everything here in the chat, but unfortunately I cannot write and read at the same time. So, do you believe that here the right-hand side and the left-hand side are the same? Do you already see this? Okay.
Professor, I have a question.
You already see this.
So
Okay.
Professor, in the equilibrium postulate, why in the
Now I have problems hearing you.
Okay, can you hear me?
At the moment I can hear you, yeah.
Yeah, I'm sorry, that was a mistake. I had YouTube on. So in this form of equilibrium, y is only b a vector and not a or c.
Mm-hmm. So this is actually not a vector. So f is the logarithm of f is not a vector, yeah. And you see that this this here is a vector.
Scalar product. Okay, yeah.
This is a velocity vector. So we make a scalar product so that we end up with everything not being a vector.
Okay.
So f is because f indicates the probability of finding a particle. So it has many dimensions. So it has 7 dimensions: time, space, and velocity. But it is not a vector. Yeah, it's only a scalar function. And back here we have something that will become the the energy. Yeah, so we have a scalar of xc1 by xc1 and xc2 by xc2, and here we need to make a scalar. We need to have some constant b.
Okay.
Okay, so that everything is in the same form. Good.
I understand. Thank you.
Okay, so then nobody answered my question. So okay, then what is this? What would this be for particles that all have the same mass? Well, it's actually the velocity, yeah. But suppose they all have the same mass, then we could say it is at least proportional to momentum. Okay. This here, velocity square, is proportional to energy. So now we have these conservation laws. So by conservation of momentum, we know that these guys before collision must be these guys after collision. The sum of the momentum doesn't change, okay? By conservation of energy, so the energy doesn't change during collision. We have the sum of the energy from these two particles before collision. And this must be the same as after collision. Okay? So now if A, B, and C are constants, then obviously the left-hand side of this, so because these guys here are equal, these guys here are equal, so then this is true, right? So left-hand side and right-hand side are exactly equal due to conservation of momentum and to conservation of energy. And this proves that this ansatz that we had here is indeed the equilibrium function. So, and now we would write this in a different format, of course. So we would have the, we'll eliminate the logarithm, and we would write this as e by the power of a, which is just a funny way of writing a constant. B, no, this is not a nice zeta. Plus c zeta times zeta. So, but this is only the general form, yeah. The actual distribution, if we put in, so basically, this is what Boltzmann got. This is what Boltzmann got, and actually, what Maxwell predicted by more physical arguments was that this is rho, yeah, the density, 2 pi r, this is the Gauss constant, by the power of 3/3, e by the power of minus zeta times, zeta minus the background velocity u squared divided by 2RT. Okay. So these two things, they are actually the same, only that in this we have some unspecified constants, A, B, C. And in this here, we have given them some physical meaning, but these both equations are of the same form. Okay. So with this, we derived the equilibrium function. Yeah. And okay, so this looks still a little bit, well, complicated. So actually, you should know this. This is a Gauss function. So this is just saying that, you know, particles follow the central limits theorem. Yeah. So the Gauss distribution is the most is the distribution with the highest probability of realization, and particles just turn to this distribution of highest probability. Okay, so this would be the more intuitive argument of arriving here. Okay, so how does this help us? Now we come to the second part of this lecture with the single relaxation time approximation. Single relaxation time approximation, which is also called the BGK collision operator. Okay, so the BGK collision operator also plays a big role in kinetic theory and in Lattice-Boltzmann in particular. BGK stands for Bhatnagar, Cross, and Crook. So this were an Indian, and South African, and an American physicist. Okay, I think that the South African was Crook, yeah, and the American was Cross, but I don't remember. So 1954. So they tackled this problem that, this Boltzmann integral that we have is difficult to solve in general. Boltzmann collision. But we know that the collision drives the distribution towards equilibrium. So, and equilibrium, okay, so equilibrium, right, either with FEQ or sometimes with F0, and I may write the F a little bit different. So now these three gentlemen proposed to drastically simplify the integral and their proposal simply looks like this. So we said that the collision operator, okay, can be written as the time change of F to collision. There's also streaming, so this would be different. So this is the right-hand side of the Boltzmann equation. And this will now simply be written as the equilibrium minus the incoming state divided by tau, where tau is called the relaxation time. Now this is much different, from the previous, from the actual integral. So if you want to have an integral now, so this would look like this. So after collision, we have the state before collision plus the integral from say t to t plus a small delta t. So this is the collision time. This would be the integral over f eq minus f divided by tau over t. Okay, I have to write t tilde, otherwise it's, Okay, so does this actually work? Let's look at the conservation laws of this. So the tau, of course, this has to be determined from, say observations, so that you match some parameters. How this works, we'll see in hopefully the next week or maybe the week after this. So today we have a few other things that we need to learn before this. So conservation laws of this collision operator. So we have this three things we have to look at. We have mass. So mass, as we introduced last time, is the integral from minus infinity to infinity And we now look at the collision operator F minus FEQ minus F, sorry, divided by tau integrated over xi, over all of xi. So the mass of the equilibrium function must be the same mass as the incoming function. Otherwise, momentum mass would not be conserved. And therefore, if we subtract these things, this will get 0. So there is no change of mass due to the BGK collision operator. Yeah, the same thing holds for momentum. So for momentum, we would have to show that F EQ minus F divided by tau integrated over the kernel xi, xi, this is also equal to 0. So as means the momentum of FEQ is the same momentum as F. So if we integrate this over the kernel xi to get the velocity, the change in velocity is 0. So the collision operator does not change velocity. And the same thing is for energy. The same thing goes for energy. So we have the equilibrium minus F divided by tau and integrate this over xi times xi over xi. And also this is correct because the equilibrium of the distribution of the the energy of the equilibrium distribution function is the same as the energy of the distribution function. So, and actually, also the ETA theorem is fulfilled by the Boltzmann, by the BGK collision operator. Okay, I'm kind of quick today. Any questions? Okay, so then there are a few more things that we have to learn before we can get more hands-on practical. And this is about something that actually we were right now using. So as I introduced last time, these guys here, these are moments. But these are not all the moments. There's a lot, there's quite a lot to say about moments. Okay, so first, from a definition standpoint, moments are integral quantities of a distribution so in kinetic theory, they give the link between the atomistic view and the continuous view. So, atomistically speaking, we have particles, and these particles have velocity xi. Yeah, so each particle is moving around in space. And they are moving around even if the air is completely at rest. Now, if we take moments, if we integrate over a large number of particles in a volume, then we get, so particle moving up and particle moving down, they will cancel each other out. And what we have in the end from this equilibrium is the macroscopic movement of the gas or the substance. So the moments give us what we actually observe, like in the world. So we see the density, we see the velocity, and we see the temperature. Yeah, and these are all moments of a distribution of molecules. And they are therefore, of course, very, very important to understand in kinetic theory, because otherwise we're not getting our information out of our simulation. And for really understanding this, we have to start with the classical definition, which may look a little bit complicated, but bear with me. This has some reason why we write this. So let's have F. Capital F of capital Xi. Let this be the the bidirectional Laplace transform of f of Xi. So let's write it this way. Yeah, sorry. Hardware f of Xi. So okay, let's use the polling. Yeah, who of you has learned about the Laplace transform? Please say yes. If you didn't learn it, say no. No, not in the chat, in the polling. There's a link on the poll. So I get one answer. What does it mean? It probably means that there's a delay in YouTube. Okay. So this is the problem with YouTube. We always have a delay in YouTube. Okay, so far I have 100% of you heard about the Laplace transform, and we got one answer. Okay, if I don't get more answers, then I will simply continue. So the Laplace transform, okay, let's say this is defined. This is defined as follows. So the Laplace transform if we define, so usually, so even more classical than this is defining it by the Fourier transform, but the Fourier transform is just the Laplace transform written down in a different way. So you can use the Fourier transform or the Laplace transform. And the Laplace transform is a little bit, requires a little bit less writing. So this is why I'm usually using the Laplace transform for this definition. So we'll have here, so this is the capital Xi integrated over Xi. And here we have this Xi that I write with the components. Now Xi, this is supposed to be a capital Epsilon, and this is supposed to be a capital Zeta. This being the complex velocity frequencies. So this sounds somewhat fancy. Yeah, this is just a Laplace transform, not in time, not in space, but in velocity. We Laplace transform the distribution in velocity. Yeah. So then, sorry. Then we define what I call countable. Countable raw moments. I will explain why this is countable. So what I call M, A, B, C, yeah, with A, B, C integer. So we can count the moments by counting up A, B, and C. Yeah, this is why it's called countable. We have here the derivative A. This is the 8th derivative of Xi, the B's derivative of this Epsilon, and the C derivative of Z of the Laplace transform distribution function with this vector at the position Xi equal to 1, to 0. So this here actually gives you the coefficients wait, my dyslexia, yeah. This gives you the coefficients of a series expansion of capital F. Capital F at the point at frequency 0. So if somebody will ever point out to you that moments are something like a Fourier transform or something like a Laplace transform, you can answer, no, they are actually the Fourier and Laplace transform. Yeah, or they are the coefficients of a series expansion of the Laplace or Fourier transform. So, but this looks pretty fancy if you actually do this. So, okay, let me put it again. ABC. If you actually do this, so f of xc. Now, and you take the derivative. Okay, you plug the derivative of xc into this equation. Yeah, so you put it into the integral, and you see the only thing that actually depends on it is here this exponential function. Then what you end up with is the wrong pen. So what you end up with is, if you take the derivatives of an exponential function, you simply get these. Oh no, this is not a vector. Sorry. You simply get these guys out. So this will be xc by a, small epsilon by b, and small zeta by c, multiplied by minus xc times xc, and this is at xc equal to 0, and this will integrate over the vector xc. And now you see that this here at this obviously is equal to 1, right? Yeah, so this will be equal to 1, so we can rewrite the entire thing. Can rewrite it as the integral from minus infinity to infinity f xc, and this xc component, the first component, the second component b, and this is the third component, and this integrated over xc, over the entire vector xc. So obviously this here looks much more simple than the original definition, yeah? And you will often hear that this is the definition. Actually, this is not the definition. This is the simplification of the definition. So this is usually how we compute it, but it is defined as a series expansion of the Laplace transform. And this is important to know, because we sometimes need some properties of the Laplace transform. Okay, so it doesn't stop here, because there are many different ways of defining moments. And also different opinions by different people. We will address two perspectives now. Yeah, one is we may have different frames of reference. And we have different orthogonality properties. So the things with the frame of reference, this is very easy to understand, actually. So orthogonality of moments, this is something that is controversially discussed in science even to this date. So let's start with the different frames of reference. Frames of reference. So there are so there are infinite many different frames of reference, but two are important, namely the Eulerian and the Lagrangian. So they play a big role here. So the Eulerian frame of reference is the laboratory frame. And this means there is a stationary observer. And the moments that we have in the Eulerian frame, these are called raw moments. So then the Lagrangian frame is a material frame of reference. This is a moving observer, and it is moving with the material. Okay, now let's write moving observer. Just moving observer, I think that's enough. So these moments here, they are called central moments. So the raw moments we have already seen. So what we derived so far, these were raw moments. Yeah, we define a frame of reference, and they say that, okay, this is now our laboratory frame of reference, the frame at rest, and we look at the moments, and okay, we get raw moments. So what we still have to see is what are the central moments. I only could write. Oh. So central moments. So the frame moves with the fluid, and if it moves with the fluid, this means that the velocity, which is the first moment, so zero moment is the mass, first moment is velocity. Defined to be zero. Okay, so the first moment gives the velocity. Yeah, so this is if we have distribution, say, yeah. So and we learned this is a Gaussian distribution, and this looks like this. So this here would be xi, and this would be f. So then this here would be the velocity. Now this is ra, yeah, and in central moments, what we do, we look at actually the same picture, but we introduce a new coordinate system where we have this here f. So this is the same distribution, but if we shift this distribution here to, say, the moving distribution, then for this distribution, let me turn this here in red. So this is the velocity in ra moments, and here in central moments, this will be 0 because we shifted the coordinate system. Okay, so this is called the Galilean transformation. Galilean transformation, where we move f, c, we turn this into an f of c plus u, right? And if we then look at our distribution, so the Laplace transform of the distribution, which is also called the characteristic function, and we integrate this, and we have here now xi, beautiful xi, plus u, and by the power of xi times capital Xi integrated over Xi. So now we changed the distribution function. We did not change the by here. However, as you see, we are going from minus infinity to plus infinity. If we go from minus infinity to plus infinity and integrate over Xi, we can shift the entire integral by this u without changing anything, because we go anyway from infinity to infinity, from minus infinity to infinity. So this is absolutely equivalent to going from infinity to infinity, minus infinity to infinity, from f of Xi e by, now we shift the integral, so we put a minus Xi minus u, so we shift the entire integral, so this u here, this will vanish, times Xi, and integrate. So if we integrate now this, we get to a new kind of moments, which we call the central moments. And which I became used to as writing them with K, as of course other people write them with different letters. Now if you integrate this out, you will end up with going from minus infinity to infinity, f of Xi minus ux. No, sorry, that was not a. There are too many letters. I'm getting confused myself. So this is supposed to be an upsilon minus uy by the power of b, and here comes a zeta minus mu z by the power of c, and this integrated over xi from infinity to infinity. Okay, so this is the definition of central moment now. And by definition, is this zero, and this zero, because these would be the velocities, and the velocity is zero. So we have to determine ux, uy, uz such that this holds. So they agree in just one moment. Density is, as we say, Galilean invariant. So M00, this is the density. The zero moment is K000. By the way, we count, so these are three-dimensional moments, and we count moments by an order, and the order of a moment is the sum of its indexes. So there is one zero order moment, three first order moments, and how many second order moments do we have? Can you write me in the chat how many second order moments do we have, so that I can see that you're actually listening? Wait, I have to count myself. Yeah. Any ideas? Okay, I don't get an answer. So there would be six. There would be M200, M02, M002, M110, M101, M011. Yeah, these are the second order moments. Okay, let's see. Yeah, okay, so we get nine second order moments. Okay, I see there seems to be a delay. Yeah, so I already answered your question, and now we get. I already answered the question myself. I don't know. It's probably on YouTube. There's a delay. So this has some communication problems. Okay, let's look at. Let's write temperature in terms of raw moments as a kind of exercise. So we have already introduced temperature as being one rho d, and here's actually r. I think I've been missing the gas constant last time. Yeah. Sometimes in kinetic theory we assume that the gas constant is equal to 1, and so we leave it out. Yeah, but to be consistent, we have to have it here. So this here was our definition of temperature. Now, what does this mean in raw moments? Let's first write out this guy here, because this will be xi times xi minus 2u times xi plus u square. And okay, so this we can further expand in 3 dimensions. So now we are in 3 dimensions. So the d is actually 3 rho r integral f of t, and these guys here will become, now this is not a vector anymore, so this is xi square plus epsilon, they're never looking nice when I try to write them, square plus zeta square minus ux xi, no, this is 2, minus 2 ux square minus 2 uy epsilon minus 2 uz zeta plus ux square plus uy square plus uz square, and this being integrated over all the 3 velocity components. And now this, so we can identify the different points that we have to compute. So this gives us second order moments. So this here gives us first order moments. Maybe I write them put them in a different color. So this gives us first order moments. And the guys back here, this gives us 0 order. Yeah. So because there's no xi, epsilon, or zeta in it. Yeah. So it's just a constant. Okay. So then we can write this in terms of these moments as, no, I have to get the right pen. You know, technology is really fun these days. So does it actually work now? No. So 3 rho r. No. Sorry. I must be very confused. So now the moment, so the first moment, so this corresponds to this guy here, plus M02 plus M002. Okay? Now coming to the first moment, so this is 2 times x M100 minus 2 uy M010 minus 2 uz M001. And back here we have the 0 moment, so I make this a bit simpler now, yeah, because I can combine all these guys together and we get 0, 0, 0. Okay, so this is what we have here. Now there's an identification M000, this is rho, M100, yeah, this gives us actually the momentum, rho ux, M010, this is rho uy, and M001 is rho U set. So you see that we have now rho U set. So we have these guys. These guys here we have here again. Yeah. So we can combine these. So this here, of course, is only in between. Yeah. And we can combine these to get 1 over rho, and we have M200 plus M020 plus M002 minus UX. No, actually we can combine this even. No, I write it in vector form to be a bit quicker. So we can combine this in vector form as U dot U times rho. Okay, so now this is actually our temperature, and you see in central moments, this guy here will simply go away. Yeah, so if we write this in central moments, it is T equals to 1 over 3 rho R, and we have K200 plus K020 plus K002. Okay, so this is one of the reasons why people may say that central moments are more natural. By the way, there was the answer that we have nine central moments of second order. This would be so if we had the entire tensor, but since a moment in x and xy, so 1, 1, yeah, is the same as yx, there's no difference, and so we have only 6 independent moments. This as an answer to what was previously written here by one of the colleagues.
Me, Professor,
Yeah.
could you explain the previous step once again after putting in the values in the pink box?
After introducing these things, okay, you see, okay, right. Let's take pink box. Yeah, I take a new pink box. We have this guy here. Yeah, where you see that M100 is the moment defining the velocity, right? You hear me? Now back here, we have, so this will, if we combine this, we'll have minus 2 ux squared times rho. But we already have ux squared plus ux squared times rho. This is this here. And we also have uy squared times rho and uz squared times rho. All with a plus. Yeah? And up here, we have them with a minus and with a 2. So this is minus 2 u squared times rho plus 1 u squared times rho. Is this what you asked? Okay, now I don't hear you anymore. Okay, if you don't answer, then I go on, because I actually want to finish this today with the orthogonality. Otherwise, I'm already running over time. Orthogonality. And the search for independence. Independence is something very important and actually difficult to obtain. So let's ask a simple question. So these moments, they're supposed to be macroscopic quantities. Yeah. So we take moments of our distribution and we get some information on the macroscopic information, something like the temperature or velocity. And the natural question to ask is whether all these moments are actually independent. And as it turns out, this is not so easy to answer and a subject of a lot of controversy, actually. Okay, let's try to get some grip to this. Okay, let's look at the equilibrium function. Rho 2 pi RT 3/3 E by C. This is now at rest, as you see. So gas at rest. Gas at rest. And now compute the second order Ra mode of one of them. So this is going to be proportional to the temperature, obviously. 3/3 E by the power of minus C 2 RT. And now, no, sorry. So Xi by the power of 2 and integrated over all the directions. And with this, we'll end up with rho RT. Okay? Okay, so we get some temperature out of the second moment. This is nice. So are they independent of other moments? Why not looking at a first order moment? By the way, there are even moments and odd moments. So 2 and 4 are even moments. Odd moments are trivially independent of each other. I'll discuss this still later. Now we look at this guy here, 2RT, and we multiply this with Xi. So now not a vector, just a component in x direction, x velocity. And we integrate this over the entire vector. And I've done this with Mathematica. Yeah, you can try to do this by hand. It's a bit annoying. So what we get out is 3 rho R square T square. Okay? So this is the temperature. So what we get out is the temperature, or if you like, the energy at the temperature square. So there's actually, this is the same information that we got out of here. So it's not independent. M2, 0, 0 and M4, 0, 0, they are not independent. Even for equilibrium. So we would like to have macroscopic quantities that are independent of each other. And the attempt that is usually done to get them independent, so attempting to make variables independent by orthogonality. So first we have to define what we mean by orthogonality. Let's have a moment M, and this is now one-dimensional, yeah? F times a kernel phi m integrated over x, and a moment n from minus infinity to infinity f over kernel n integrated over x. So then the kernels phi m and phi n, this is not a nice n, and phi n are called orthogonal. So this is after the crash. So the kernels m and phi m, the kernel phi m and phi n are called orthogonal. Let me put this on. Orthogonal to the weight No, they are not orthogonal to the weight. Now this is orthogonal with weight. Okay, can you turn off your sound for the time being? And
yeah, sure, sir.
Orthogonal to the weight. Let's call it W xi. Yeah. If 0 equals to this integral from infinity to minus infinity to infinity W xi phi m phi n integrated over xi. So, and now we say that if, so that's the definition of this orthogonality, but it's only valid with a certain weight. So if phi m and phi n are orthogonal, then they extract different information from the distribution. So independent. Independent information from WC. So, and this leads us, sorry when this gets a little bit longer, but I want to finish this here with the, oh no, I think this is a good way to stop, and we'll continue with this later. Okay, thank you very much.